Okay, so now let's look further at J.J. Thomson's apparatus and how he used it to discover the electron. Remember, we have these unknown cathode rays. Forget the fact that we know these electrons. We have these unknown cathode rays, which are coming out of, the electron gun. We're sending them between plates where we can put a voltage. And what I didn't say last time is I said that results in an electric field, right? It results in an electric field, which is up or down, an electric field which is up or down, electric fields. We'll talk about the relationship between the voltage and electric field in a little while when we need to. But right now we just understand it results in an E. We know that we can put a magnetic field in or out of the page by putting coils outside. But now J.J. Thomson, after he used the magnetic field, he used that to measure the speed of the electrons. Now we know the speed of the electrons. We are going to turn off the magnetic field and just look at the deflection due to the electric field. So we can look at the deflection due to the electric field. And we're not going to use the second pair of parallel plates. We're only going to use this right here. Okay, so we've used the velocity selector, so we know V sub x. And now we are just going to turn on only an electric field, look at the deflection, and see what that tells us. So I didn't say before, but should be implied, that what J.J. Thomson and scientists realized that these cathode rays were charged. Somehow they had charge, because if they applied electric and magnetic fields, they deflected. So thus they were charged. I mean, that was understood. The Lorentz force is understood, right? That the Lorentz force is QV cross B plus QE. But we still don't know what the cathode rays are and whether it's just a whole bunch of different kinds of particles or whether it's whatever. We don't know anything about them other than they're charged. Okay, so what J.J. Thomson did was he put only an electric field. So I'm still sort of trying to draw this in 3 dimensions. So we've got some potential difference across the plates. And let's just say that that gives you an electric field that is, let me just use the same as my notes. Let's say that electric field's in the downward direction. So we're going to apply an electric field in the downward direction. So that is going to make this charged particle, which is going at some velocity, v sub x, we'll try to make that a small script v, is going to make it deflect while we're going through these plates parabolically, and then when it's done going through the plates, it'll go in a straight line. Okay, let's look at that deflection. Right, this is just electric deflection, electric force, and we know that the electric force in magnitude, the electric force in magnitude is QE, charge times the electric field that we applied, and that electric force must equal m times a, the acceleration in the y direction. We'd already called the direction of the electron the x direction, so the y direction is the direction up or down. What I want to determine here is, remember, we've got a screen over here where we see the cathode rays hitting. The cathode rays are hitting the screen over here. And this line, after it leaves the plates, let me just make that some color. This line here is a straight line. Whoops, it's not meant to be an arrow, but that's a straight line. That's not meant to be an arrow. I'm not going to change it right this second. Hold on. I drew a straight line. Once it is no longer being deflected, it's just going to go in a straight line again. But when it's deflected deflected parabolically. So what we're looking for, actually, is the angle at which it's deflected. The angle, the angle between its original path, where it would have gone if it had gone straight, and its new path where it ends up, right? So this angle here, whoops, that was not needed. This angle here is what we're looking for, theta. Okay, and in order to find that angle, what we want to do is find out how much has been deflected while it's between the plates, and we're going to do that with a Newton's second law and kinematics review, a new application, but we're just reviewing Newton's second law and kinematics. So, while it's between the plates, we have this force relation. Newton's second law says that the net force equals ma. And therefore, the acceleration in the y direction, the acceleration that it gains, is qe over m. So we actually want to find out how far it has gone off path, right? Which would be which would be the distance. It's kind of hard to draw it here, but the distance that it, whoops, that was not what I meant to do. The distance, stop. We're interested in finding how far it has deflected while it's moving between the plates. I'm calling that delta y. And we know that delta y is equal to 1/2 a sub y t squared plus v0 yt's, kinematics. That's how far it's deflected while it's between the plates, just while it's moving between the plates. We know that v0y is 0 because it was originally going just in the x direction. So therefore, in order to figure out how far it's deflected, we need to know how long it takes. So therefore, we want to look at the x equation. Delta x equals vx times t. Vx times t. Vx doesn't change. It's not accelerating in the horizontal direction. It's constant velocity. So we're going to look at that, and we're going to see, okay, therefore t equals delta x over vx. Now remember, we know vx because we measured that using a velocity selector. And do we know delta x? What is delta x? Delta x is the distance that it travels while it's between the plates. Because remember, we want to know how far it deflects while it's between the plates. So delta x is just this distance here, the length of a plate. And we also know that the next kinematic equation, I sort of did them out of order, vy equals v0y plus ayt. So now we can solve these kinematic equations together. Actually, I'm not entirely sure I needed delta y. In order to figure out the path that it's following, I want to know the velocity in the x direction and the velocity in the y direction. Right? The velocity in the x direction and velocity in the y direction is going to give us the velocity after it goes through the plates. So I want to know vy and vx. I guess I didn't need to know delta y, but it doesn't matter. So therefore, vy is ayt because v0y is 0. Okay, I'm going to write this on the next page.